Okay, this is a Bioengineering 599J. We are in week number 5 already of the spring quarter. Today we have a special speaker, Dr. Robert Renneman, who is a professor of physiology at Maastricht University in the Netherlands. And he received his medical degree in 1961. And he also received his PhD degree in 1968 from University of Utrecht. And then he came to UW to work with Dr. Bob Rushmore and his group for about 18 months. And he has been coming to Seattle on a regular basis ever since, in the 70s and in the 80s. And I met him for the first time in 98 or so. And he has numerous achievements and honors. And if I read them all, he will not have any time, so I will just spend 1 minute. He has 394 journal papers and 159 books, book chapters and conference papers, and 450 abstracts, and 59 PhD, the thesis. He supervised 59 PhD students. And he is a fellow of the International College of Angiology, elected fellow of the European Society of Cardiology, and fellow of the circulation section of the American Heart Association. And he was president of the Federation of European Physiological Sciences. And most recently, since May of 1999, he became president of the National Academy of Science in the Netherlands. Dr. Renneman will give us a seminar with the title of Wall Shear Stress in Human Arteries, its relation to artery wall thickening. Dr. Renneman.
Thank you very much, Dr. Youngman Kim. It's a great pleasure to be back in my second hometown, Seattle. So if I retire, I don't know when, then I might become forever, but I love it here. The weather is the same, only the climate is a little warmer. What I like to do with you is to share with you the data we have collected actually in the past 3-4 years on wall shear rate and wall shear stress in humans. As you all know that the endothelial cells lining the arterial and venous system are exposed to mechanical forces, pressure, stretch, and a very important one is shear rate. I don't want to go into detail on the mechanisms involved now in shear, on acute and more chronic regulatory mechanisms, but most of the data available have been obtained in vitro experiments, for the very good reason that until recently it was quite impossible to determine shear reliably, non-invasively in animals and in humans. And what we have done, as many others, is to estimate mean wall shear rate, assuming a parabolic velocity profile and measuring mean velocity in the artery and the diameter. That's an approximation, but way off actually, because we all know that a velocity profile in an artery is never a fully developed profile. It never comes to a parabola, for the very good reason that the entrance length is very short and we're dealing with pulsatile flow conditions. And that also holds for the small arteries, 15-20 micrometer in diameter, as we showed. So the velocity is flattened in the center and the gradient is really near the artery wall. And so if you want to estimate shear non-invasively, you must be able to determine the velocities close to the wall accurately. And that's some kind of a problem for two main reasons. The first reason is that the spatial resolution is limited because of the finite size of the sample volume. You can't make your sample volume smaller than about 250 micrometer. Delta F times delta D is constant, so you get spectral broadening and noise, so that's a limitation. That's the best what you can do with ultrasound is around 250 micrometers from the wall. But the more important problem is that you all know that the artery wall is a hell of a reflector. And the amplitude is 30 to 4 times higher you're getting back from the wall than from the moving red blood cells that you want to detect and the velocity determine. So in the old days, we all used high-pass filtering to get off the vessel wall reflections, and you got rid of them, but you also lost all the low velocity information near the wall. To overcome this problem, Peter Brunson in our institute, when he did his PhD thesis with Arnold Hooks and me, he got the idea of adaptive filtering. And adaptive filtering actually is taking into consideration the time distribution of the signal you're getting back, because from the wall is moving. So you don't get one signal at a particular frequency, but you get a frequency distribution back. So what he did and considered to shift the temporal distribution back to a high amplitude around 0 frequency, and the shift being determined by the mean frequency of the spectrum. And I've written that down here, what we're actually doing and what I just told you. And when we do that, we shift it back to 0 frequency, high amplitude, then use high-pass filtering, and you eliminate the high reflection from the vessel wall and maintain the low velocity information. And this is actually shown on the next 2 slides. Here you do have the A mode of the vessel wall, the RF signal. I come to that back in a moment. Anterior wall, posterior wall, and here is the velocity information. So this is a tremendous reflector. And when you determine the RF matrix of the signal you're getting back in M mode, I will show you in a moment. Then you can see the bands here of the vessel wall, masking the low velocity information. And with the adaptive filtering, we're maintaining all the low velocity information, eliminating the vessel wall reflections, and the matrix is cleared from vessel wall reflections. So we have a nice signal, and we can do the RF correlation, and I'll show you in a moment. We do the RF correlation across the M mode, and you get a 3D spectrum. So this is the principle of the method we have been using to assess shear and velocity distributions. And we use classical M modes. You can hook up our system to any B mode that you want to use. We use ATL, we use our own systems, we use Biomedical, and you can link it up. And in this particular case, showing the carotid artery. Then we take a B mode image of the vessel we're looking at. In this particular case, the common carotid artery. Here is the bulb, the proximal part of the internal, which is widened. Here the external. And then we can select any side of measurements along the vessel using the flow divider as a reference point. And then we switch to M mode. Here the M line is depicted. And then the whole processing is done in the RF domain along the M mode. And the first M line activated is displayed on the screen, because we have to identify in our processing the anterior and posterior wall, for the very good reason that if you want to do the adaptive filtering, you have to track the vessels throughout the cardiac cycle. So that's the only thing what we do manually, is to put a cursor on the anterior posterior wall so that we can track the anterior wall during the whole measurement procedure. And this is shown here schematically again. Anterior wall, posterior wall. This is the sample window for tracking the anterior, and this one for the posterior wall. And here we are sampling more or less continuously along the M lines and getting the information, and do RF cross correlation. A few years ago we still did Doppler correlation, but RF correlation has several advantages. It's independent of the RF sample frequency, and most importantly, it's still accurate when you're dealing with very short temporal estimation windows, and I'm talking here about 1 to 2 milliseconds like in color-coded systems. So we feel that RF correlation and RF processing is the way to go. And in this way, we do get a 3D presentation of the velocity distribution. velocity on the vertical axis. This is describing the depth anterior to posterior wall, and here is the time. So what I've depicted here is the velocity distribution in systole, in diastole, and there the next beat comes up. And what we do is at any site, at any instant of time, we take the first derivative of the velocity, the dV/dr. And then we take the maximum of this first derivative as the reading for shear rate. We present the peak during systole, calling it peak wall shear rate, and then we take the time average value over one cardiac cycle as the mean. And I like to draw your attention to the fact that when you determine mean wall shear rate, that diastole is an important determinant of the mean wall shear rate. People try to forget that and always think, oh, it's very high in systole, but when you look at the time distribution, the major determinant of mean wall shear rate is shear rate in the diastolic phase of the cardiac cycle. And that's important for the rest of my talk. So here I'm showing you the shear distribution in that artery derived from the velocity distribution on the previous slide. Here is the peak in systole near the wall, what you would expect, but there's the velocity gradient is. Both walls, the next cycle, and here is the diastolic distribution of shear. So we determined the intersubject infrasession and intersubject intrasession coefficients of variation day 1, day 2, day 7. And you see that they are acceptable. They are running between 10 and 50%. In the intersubject intrasession, they are slightly higher. But that learns us that we have to take 16 recordings at the same site to come up with an acceptable coefficient of variation. And we can do that in a very stable way. So the velocity profiles recorded with the probe in the same position are very stable. But we always take 16 recorders at a given site. So the next question, when you want to calculate wall shear stress from wall shear rate, is the value of the viscosity that you're going to use. When you really want to have wall shear stress, it would be appropriate to determine wall shear stress from plasma viscosity, because that's the viscosity wall is seeing. But the problem is that our sample volume of 250 micrometer is substantially larger than the layer of plasma flow along an artery, which is only 7 to 8 micrometer. So in the small vessels, in the arterioles, we always have used plasma viscosity because we come as close to the wall with our markers as 1 to 3 micrometer. But here we have been using whole blood viscosity for the very good reason that our sample volume is large as compared to the thin plasma layer. So the data I'm going to present you are with whole blood viscosity. So when you look at the theory, and quite a few people have worked on wall shear stress in the theory, and the best papers, I think one of the best was by La Barbera in Science in 1990. And when you look at a properly designed arterial system, the Murray's law should apply. And Murray's law is that the third power of the daughter, the sum of the third power of the daughter branches is equal to the third power of the parent branch. And this is the properly designed arterial tree, and it has been shown in many arterial trees that it roughly holds. We did it for the coronaries, and we're running there at 2.8 and not at the third power. And this is based on the theory of minimal energy discharge along the artery. So wall shear stress, that's what the theory predicts, is equal everywhere along the arterial tree. And other studies done by, among others by Kamiya, they indicate that it should be around 1.5 Pascal as a level. So let's look at those two. And we assessed mean wall shear stress in the common carotid artery, the femoral artery going to your leg, the common one and the superficial one in the brachial artery. And when you look at those data, then only in the common carotid artery the value is like the theoretically predicted one, 1.5 Pascal, 15 dynes per square meter. But when you look at the femoral artery, the common, it's substantially lower than mean wall shear stress. And I'll come to that in a moment. Even lower in the common than in the superficial artery. And the brachial artery, I just put the data up, we just finished the measurements very recently, it's around 0.9. So there's a very significant difference. So this part of the theory doesn't hold. That it's equal and the same everywhere, and that is running around 1.5 Pascal. There's another aspect predicted by the theory, that shear stress on the walls of the arteries is constant. In other words, it is the parameter to be regulated. And in a variety of studies by a variety of authors in all kinds of parts of the arterial system, it has been shown that when you increase the velocity, that wall shear rate and wall shear stress doesn't change an awful lot. And that's because of the diameter regulation with shear. When your shear goes up in larger and smaller arteries, EDRF NO is produced and prostaglandins are synthesized that are dilating the vessels. So that's an acute regulating mechanism. And it also holds for the smaller arteries as we showed, but there prostaglandins are getting more important than NO. Well, in the larger vessels, NO is the most important mediator. But what was not well known is what is the effect of viscosity. If I change viscosity in a human being, what is then the response of mean wall shear stress? We did a crude experiment, and we did look at patients with renal insufficiency who went for hemodialysis 3 times a week. We looked at mean wall shear rate and mean wall shear stress before and after hemodialysis, because as you may know that in hemodialysis viscosity goes up very significantly, and then we looked at the shear response under those circumstances. It's a crude experiment because you're also changing blood pressure. Plasma viscosity before and after, whole blood viscosity before and after, and hematocrit before and after, so it's going up. And when we looked at mean wall shear rate and mean wall shear stress, they didn't change, despite a substantial increase in viscosity. So the human being apparently is able, among others through a change in diameter, to keep the mean wall shear rate and mean wall shear stress stable when you have acute interventions, not only when the velocity changes, but also when the hematocrit changes. The other thing we did, because it was to our great surprise not well known what happens to mean wall shear stress as a function of age. Here I've plotted mean wall shear stress as a function of age in the common carotid artery. The continuous line are males, the dashed line are females, and 1.5 in men, slightly lower, significantly lower, but slightly lower in females. There was a slight decline with age, not significant in men, but it was significant in females. So there is a slight effect of age. We did the same in the femoral arteries. The wall shear stress here in the superficial femoral artery and the common femoral artery, which is lower as I showed you. And there's no change whatsoever with age. So again, as a function of age, wall shear stress is rather well regulated. So we felt rather confident that we could measure shear in femoral and carotid arteries in humans. And as you may know, there have been, Alan was that I think in the early 70s, we and others performed experiments to look at the velocity distribution in pipes, glass pipes. And Cy Kleikoff was the first to show indirectly that in the areas where you could expect low shear, the wall was thickened. He did that with autopsy specimens that he correlated with the flow distributions that he saw in the glass pipes. So it has been hanging around that there might be a relation between shear and wall thickening, so that in low shear areas the wall is thickened. There has been some in vitro data among us at Harvard, and Bob Neerum recently showed that in flow chambers, isolated cells, when shear is low, then you get an upregulation of growth factors, upregulation of endothelin, and expression of integrins. So there is increasing evidence that wall shear has an effect on wall structure and even on wall function, because as you may remember that the sites of preference for atherosclerosis are also at these sites. And I don't say that wall thickening is a prerequisite for atherosclerosis. Although they are related, I don't think that they are causal related. And I'd like to discuss that with you if you wish. So we said, okay, we now have the possibility to measure shear along the arterial system and in bifurcations. So we like to relate it to wall thickness. And when you use a classical B-mode image, you can easily distinguish intima here, the media here, the adventitia there. But as you show here on the anterior part, intima can be distinguished media, but it's very difficult to distinguish the adventitia from the surrounding tissues. I know that several people are working on it, and Kurt Beach is looking into it. But therefore, we still rely on intima media thickness as an indicator of wall thickness. And what people have been doing, including our group, is to measure intima media thickness along a certain stretch of artery. But we also saw that there is tremendous heterogeneity in intermediate thickness along the artery. So we said we like to have a technique that we can measure very locally, 0.5 to 1 centimeter apart along an artery, so that we can relate it to the local shear. So we developed a technique to automatically assess locally intima media thickness. And it's depicted here schematically. Again, the RF signal, blood, intima, and this is media, adventitia, the reflections you're getting back. And what we do, we take a relatively large sample volume that is at least covering the blood intima transition and the media adventitia transition. And then we take the instantaneous envelope of the RF amplitude signal. Then we phase align the signals to eliminate or reduce vessel wall motion artifacts. And then we take the time average of this instantaneous amplitude, and we take the time average in systole to reduce speckle interference and to enhance the signals that you're getting back from your interfaces. And the next slide shows such an instantaneous time averaging. Here the transition from blood to the intima, and here from the media to the adventitia. So we do edge detection at 50% and at least 50%, and it should be at least a ratio of 1, so that we do have confidence in assessing IMT automatically in the sample window. And when we looked at the intersubject differences between 3 measurements, the differences are plotted here, then when you average everything, the standard deviation is around 0.044 millimeter, which is relatively small if you consider that at your age the thickness is about 0.6 millimeter. At my age it's around 1 millimeter. So we are thickening with age. So this is pretty good, we feel. So we said, okay, we do have the technique to assess intima media thickness locally, and we can assess wall shear locally. So then we did two separate studies and looking at the relation of shear and intima media thickness in the carotid bifurcation and the femoral artery bifurcation. This is schematically shown what we did in the carotid bifurcation. We are, the present state of the art, we're not able to measure shear accurately right in the bulb because of the recirculation occurring there. We're working hard on that. So we took the wall shear assessment just proximal to the flow divider, where we also assessed IMT. It's in the same probe, it's in the same system. We also can measure distensibility if we want. And we took the same measurements 3 centimeters more upstream. This slide shows you the velocity distribution and the shear distribution just before the bifurcation. And this is the distribution 3 centimeters more upstream. And what we did on this slide is a slightly complicated one, but we have to swallow it. What we did, we plotted the shear near the bifurcation as a percentage of the shear more upstream. So the percentage is plotted here. So if they would have been the same, the percentage would have been around 0. But what you see is that the shear in most of the cases is substantially lower near the bifurcation at point B than more upstream. So even when you consider a stretch of artery around 3 centimeters, then there is a difference in wall shear rate and wall shear stress. And why is that? We feel it has to do with reflections. This is the velocity distribution recorded very close to the bifurcation. This is the side of the external carotid, it's the external part. Here is the side of the internal carotid, it's the internal side. And you can see clearly here that there is a good reflection coming from the external carotid, which has disappeared and which has been damped out 3 centimeters more upstream. So when you look at the velocity profile, you can see that there is also a difference in development and difference in shear distribution. So this explains, to our opinion, that the wall shear rate is lower close to the bifurcation than more upstream. So then we related these findings. So if this difference is functional, then we should find a difference in intima media thickness at these two sides. So again, plotted in the same way, the intima media thickness near the bifurcation B as a percentage of the intermediate thickness at point A more proximally. And here you can see that at nearly all sides the wall was significantly thicker near the bifurcation than more upstream, there where wall shear rate and stress were lower. So that indicates that the old theory of Cyclakoff holds, and that has been demonstrated now then in vivo situation, but even at relatively small differences in wall shear stress. So in a following study, we repeated the same experiments in the femoral artery bifurcation, schematically shown here. Here's the flow divider, common femoral artery, the deep femoral artery, and the superficial femoral artery. And we measured in the common femoral artery 3 centimeters roughly upstream of the flow divider, and in the superficial roughly 3 centimeters downstream of the flow divider. This shows you again velocity distribution in the superficial femoral artery, velocity distribution in the common femoral artery. You see already the differences in shape. And these are the shear distribution in the superficial femoral artery, in the common femoral artery. And striking difference, if you remember the one in the common carotid artery, that the flow is mainly in systole and even showing some negative peaks in diastole. So when we looked at the wall shear stress in the common and in the superficial femoral arteries of the volunteers at rest, in young and old ones, those are the data, the endpoints of the graphs I showed you before, that in the common femoral artery, the mean wall shear stress is 0.38 in the average, and it's 0.54 in the superficial femoral artery, and those differences were significant. It's not a great difference, but the differences were significant. And the same holds at older age. Those volunteers were 15 to 60 years of age, and there you see also a difference, 0.3 versus 0.6, and this difference was also significant. So wall shear stress is lower in the common femoral than in the superfemoral artery. And this is again due to the reflections. I think this is depicted here. When you look at the common femoral artery, you get your velocity in systole and you get an early backflow coming from the deep femoral artery. If you remember, when you record here, the common femoral artery is not seeing only reflections from the superficial but also from the deep femoral artery. So there's an early one coming from the deep and a later one coming from the superficial femoral artery. While in the superficial femoral artery you have only one reflection. The main one is coming late from the superficial. So we think, remember, that the diastolic phase is the most important part of the cardiac cycle as far as the level of mean wall shear rate is concerned. So the diastolic part determines greatly what is happening to your mean wall shear rate. So the proof of the pudding was, if we are right, that those reflections are important, that we dilated the vascular bed through a reactive hyperemia response, and then you know that the reflections disappear, and then the level of wall shear stress was 1.3 Pascal, so pretty close to the theoretical one and pretty close to the one in the carotid arteries. So reflections are important. And then remember the small differences in wall shear stress, 0.3, 0.6, 0.4, 0.55. And then we looked at intima media thickness there. Plotted in the same way, intima media thickness in the common femoral artery as a percentage of the intima media thickness in the superficial femoral artery. And you see that in most cases, the intima is thicker, intima media complex, thicker in the common femoral artery than in the superficial femoral artery. So again, at rest, the low mean wall shear has an effect on intima media thickness, despite the fact that when you're exercising, the wall shear stress is up to the theoretically predicted level. So at rest, those levels are apparently having an effect on the structure of the wall. So in summary, I think that I've shown you that wall shear stress is lower in the femoral than in the carotid artery bifurcation, and different at various sites in these bifurcations, to our opinion, due to reflections and differences in reflections. In these bifurcations, wall shear stress is associated with larger intima media thickness. And mean wall shear stress at rest changes only slightly with acute changes in blood flow. I didn't show you those data because they're very well known, but also with viscosity, and it doesn't change or is only slightly with age. So based upon the theory that the level of wall shear stress is the same everywhere along the arterial tree does not hold. Second is that it's well regulated, that's for sure. And that is in accordance with the theory. But it's at the level of 1 Pascal along the arterial tree is not true either. So that brings you to a warning, actually, because when you review the literature on isolated cells and exposure to shear, everybody is taking some kind of an average level. Although the more modern studies are more accurate, but several of the studies even don't distinguish venous from arterial shear stresses. And if it's shown in the microcirculation, the venous stresses are a factor of 4 lower than on the arterial side. So you have to be careful in setting up your experiments and expose the endothelial cells to the shear they're normally seeing. Having said that, this is the group I've been working with for quite some time. Arnold Hook is the professor of ultrasound technology. He did his PhD with me, and he's the smart guy who is accomplishing the rough ideas I have on my bike and what we should do next. But he has to make the system, and he does it very well. He's a hell of a good engineer, but also a good biologist. Peter Brands, an electronic engineer, did his PhD with Arnold and me, and he worked with us for about 15 years, but he was bought by the ultrasound company we're collaborating with, and that's fine. He is doing an excellent job, and John is another electronic engineer working with us for 10 years. Lillian is the postdoc who was heavily involved in the shear measurements. She's still with me, and she just got a new baby last week. So Christine was the PhD student involved in all these shear measurements, like Steve Samio. Steve will defend his thesis next week. Christine did it 3 months ago. She is an MD, PhD now. She's training as an obstetrician, the mother of 2 children, and Steve is a resident in orthopedic surgery. Thank you.